Hello, my name is Roy Werger, and this is my Lab 5 titled Magnetic Braking with Faraday. The purpose of this lab is to observe a magnet falling through a conductive tube of aluminum foil and record the data, create a computational model based on Faraday's law, Savas law, and Newton's law of motion using Python, and then compare the computational data and model with the observed data. In our findings, we saw that the average observed time for the magnet to fall through the loop was 1.268 seconds, and then with a magnetic dipole of 1.5495 m squared from lab 3, the predicted time for the computational model is 1.31 seconds, and then the magnetic dipole of 1.5240 m squared was needed to match the observed average time. Faraday's law is the equation that relates the integral of the dot product between the induced electric field and the length of the outer edge of a closed area to the negative derivative of the magnetic flux, and which is represented by dB over dt, negative. Beard-Savas law is the equation that gives the magnetic field produced due to the current carrying a segment, and we found this equation in lab 3. And then lastly, the change of magnetic flux represents the time derivative of the magnetic flux of the dipole and its derivative of the dB over dt magnitude shown in the Faraday's law. In this lab, we also used the formula for Ohm's law to calculate the relationship between voltage, current, and resistance. Then the magnetic force of a wire loop equation represents the cross product of the current multiplied by the L vector with the magnetic field, where the L vector has a magnitude equal to the length of the wire, which is 2 pi r. And then Newton's third law basically just states that every action has an equal and opposite reaction, and this concept is a point for this whole lab. In this lab, our system is the aluminum tube and the bar magnet, and the surroundings is everything else. In this experiment, I utilized the magnetometer app on my phone to find the north pole of the magnet, and then record the mass, foil, radius, and length of the tube, and then I propped my phone to record as I dropped the bar magnet through the aluminum tube and repeated this trial 5 times, and then I used the video footage to determine how long the magnet took to fall through the loop tube for each trial, and then found the average time between the trials. In this lab, we assume that air resistance is negligible, and gravity and the magnetic force from the aluminum tube are the only forces acting on the falling magnet. Here's the observation results from the lab. Here we recorded the properties of the tube and the magnet, and I also saw that between the 5 trials, the average time interval was 1.268 seconds. In this lab, we cannot use a ferrous tube because the ferrous tube contains iron, which has magnetic properties. So if the bar magnet was dropped in the ferrous tube, the induced magnetic field from the iron will be interfered and skew the data. And then when the magnet falls through the aluminum tube, it is slower than what it will normally fall in free space due to an upward magnetic force acting on the bar magnet due to the induced current on the aluminum tube. Here's the initial conditions and constant part of the Gloucester code. Here we have the U0 over 4 pi constant, the resistivity constant, Mg, in addition to the properties of the aluminum tube and the bar magnet. Here we can also see that we have the bar dipole moment calculation shown in line 77, and then also that the initial velocity is 0 as we're dropping it from rest. In this part of the code, we have the magnetic field equation, which we derived from lab 3, and the magnetic flux equation. By going through these two equations, we're able to determine how the bar magnet moves through the aluminum tube. Here's the code for the simulation loop, which calculates the force of the magnet on the loop and the force due to gravity to find the net force. The loop also updates the velocity and the position of the magnet. Here are the results from the computational model. The result based on the magnetic dipole moment from lab 3 is shown on the left. On the right, the magnetic dipole moment was altered to 1.524 m squared to match the average observational time. The time plot between the two dipole moments are almost identical. Here's the interpretation of the data from the computational model. To answer the first question, from above, the red current corresponds to the counterclockwise direction and the blue current corresponds to the clockwise direction. This can be proved by using Lenz's law. To answer the second question, when a magnet is flipped, it will still fall slower through the tube than if it was falling without going through the tube, but the current would still be flipped. To answer the third question, the total time in tube in the experimental model compared to the computational model was almost the same, as the computational model was only larger by 0.042 seconds, and the graphs that were produced were almost identical even before I modified the dipole moment in the computational model to match the experimental results. The computational system can be made more accurate by splitting the tube into more rings or reevaluating the magnetic dipole of the magnet in the experiment. And to answer the last question, the shape of the velocity versus time plot tells us that at the beginning, the gravitational force and the magnetic force are unbalanced as the velocity either increases or decreases, and then as time passes, the force becomes balanced and the velocity remains constant, and then towards the end, the forces become unbalanced again as the gravitational force becomes larger than the magnetic force. Some possible errors include the incorrect magnetic dipole moment due to an error in lab 3, error due to the rounding in measurements and calculations, and contact and friction between the magnet and tube, which would cause an increase in time for the magnet to pass through the tube. The following fixes for each of these 3 errors are shown below. What if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? Due to Ohm's law, a near-zero resistivity results in a large induced current and would create a greater force on the bar magnet to prevent it from falling. Therefore, the magnet would therefore fall at a lower speed because the force on the magnet from the loop will be closer to the magnitude of the gravitational force. What if holes and slots were cut into the tube? How would this affect the ring currents in your model? The holes and cuts will disrupt the continuation of the rings in the aluminum tube and allow the induced currents to flow around the tube as the magnet falls. This disruption will reduce the induced current and therefore reduce the magnetic force on the force by the loop due to Newton's third law. Therefore, the magnet will fall at a faster speed because the magnitude of the force on the magnet is less than the force of gravity.